We argue that besides objects, it is also crucially important to come up with a suitable representation of the 3D physical space within which objects are arranged and organized. Most of the time, computer vision researchers have tackled the problem of understanding an unknown scene by representing objects as 2D bounding boxes, and by assuming that these lie in the flat 2D world, that is, the retinal planes. These are often interpreted as canvas upon which objects are organized. The interplay among objects is thus modeled as simple 2D relationship: above, below, 10 pixels on the left, 10 pixels on the right. We argue instead that we can make much better sense of the perceived environment if we acknowledge the fact that objects live in a 3D world, not in the 2D retinal canvas, and their arrangements are modeled as 3D relationships. Why is this important? This is critical for a number of ecological and evolutionary reasons. Psychologists suggested that infants begin with a perceptual similarity space, and only much later this is transformed through learning. Example: if you are really hungry and you can pick up only one fruit from this table, which one would you pick? Let's assume you've never seen these two fruits before and you don't have prior knowledge about the size of the fruits. If you measure their size in the image, the cherries looks bigger. So would you pick the cherries? No, you would pick the watermelon because you have learned that objects that are far away look smaller, and you know that this object is far away because you are relating it to the far end of the table, which accounts for the space in this scene. So a 3D representation of the space is crucial in that it helps the agent to make standard comparisons among objects in the scene. Psychologists have long time stressed the importance of the integration object space. In the number of seminal studies by Biederman and colleagues, it was shown that humans have learned the typical relationship that occur between objects and space, which can be described by location, size, support, to name a few. Biederman's experiment showed that when these relationships are violated, like in these two examples, humans recognize objects much less accurately or efficiently. So scene understanding is really an interplay between space and objects. My group has investigated various characterizations for representing the 3D space and for explaining how all bits and pieces of visual information can be structured into larger units of perceived objects and their interrelations. So how to represent a 3D space? As we mentioned at the beginning of this talk, traditional approaches often represent the space as a dense collection of 3 points. This is clearly superfluous. If one wants to capture the interrelation between object and space, a much more compact representation may be sufficient. For instance, the 3D space can be compactly described as a collection of surfaces. If we are talking about an indoor environment, this can be floor, walls, ceiling. In such 3D space, physical objects such as a chair, a sofa, or a desk can be easily arranged and organized. How to estimate such surfaces in general conditions? Many options are possible. Very recently, we have shown it is possible to learn to infer the geometry of indoor scenes, floors, walls, ceilings, in a pure end-to-end fashion using a deep learning architecture. This architecture maps RGB pixels to one of those geometrical classes. An ensuing optimization phase guarantees that this labeling process is globally and geometrically consistent. Here we see some results. Given a single image, like this one, our method can infer the 4 major geometrical classes: floors, wall left, wall right, ceiling, each associated to a different color code. Here we can appreciate the inferred geometrical classes overlaid on top of the image. Other examples are shown here and here. Quantitative evaluations on the LSAN dataset shows superior performance compared to 2 baseline methods. Performances are measured in terms of pixel error in associating the 4 class labels. If you visit our project webpage, you can play with the demo where it is possible to upload images of rooms and obtain a 3D layout estimation in return. Now, equipped with any of those simplified representations for the 3D space, for instance made of a number of planar surfaces, the question is how to model the interplay between object and space and objects and objects. One idea we explored is the concept of 3D geometrical phrases. Similar to sentences that relate words in fixed grammar structure, 3D geometrical phrases capture the typical geometric and semantic relationships between groups of objects that frequently occur in the 3D space. On the right, we can see an example of geometrical phrase, the dashed line, that relates the two sofa and the coffee table. Using an approach that leverages max margin learning equipped with a novel latent completion algorithm, we show that it is possible to discover a dictionary of useful geometrical phrases from a large training set in a way that this process is semi-supervised and allows to make the geometrical phrases compact and view invariant. So given a query image that has never seen before in training, we can use our dictionary of geometrical phrases to jointly estimate the most likely 3D space, described by floor, walls, and ceiling, as well as the objects inside, a table with 4 chairs. Different color codes correspond to different categories. The dashed lines indicate the geometrical phrase connecting the objects of interest. So far, we have explored ways for modeling the interplay between objects and space for a specific environment such as a room. This concept can be further extended to a larger scale. Objects such as walls, doors, can be seen as elements of a space which is a room. In turn, rooms, corridors, hallways can be seen as elements of a larger space which is a building. So we have shown that it is possible to turn these large-scale structures into informative and functionally meaningful building elements called building information models, or BIM. Building elements include, for instance, corridors, rooms, hallways, as well as walls, tables, and windows. The key innovative aspect of this work is that BIM parsing are evaluated at unprecedented large scale, following a procedure that is fully automatic and hierarchical. We have successfully tested our BIM parser on several types of buildings which are part of a new dataset we have created and made available to the community. These datasets include 3D point clouds of 6 large buildings. Each building contains 450 rooms and thousands of building elements. Building elements have been manually annotated and labeled. For more details, please visit our website. I expect that our BIM parser will play a key role for automatizing large-scale information management, improving performance analysis, and making assessments in terms of sustainability of the construction design. Moreover, BIM parsing can also be very useful to build semantic maps that can be used by robotic systems to intelligently navigate through an indoors environment. Our work on large-scale information management is related to a long-standing effort in my group, connected computer vision with construction monitoring and information processing of construction sites. For centuries, construction managers have monitored construction progress by manual data collection that is highly time-consuming, extremely expensive, and erroneous. It has been estimated that an improvement of as little as 1% can lead to up to 900 millions of USD in savings in construction business. By leveraging our work on 3D scene analysis, we have proposed an integrated framework called 4-dimensional augmented reality, 4D AR, that enables automatic tracking of structural changes, allowing data to be collected easily, cheaply, and objectively. 4D AR allows to obtain two things at the same time: an accurate metric reconstruction of the geometry of the site from pictures, the identification of the important semantic phenomena such as pillars, walls, scaffolds. By comparing such semantic reconstructions with S-plan model at any given day, We show that it is possible to automatically predict elements that are constructed on schedule, ahead of schedule, and behind schedule, as well as enables the automatic tracking of structural changes. Because 4D AR has initiated a paradigm shift in the civil engineering community, it has been recognized by numerous awards, including the prestigious James Cross Medal from the American Society of Civil Engineers in 2013. To recap, so far we talked about representing the 3D physical space. This provides the context within which the physical objects are arranged and organized. We also discussed how to model the interplay among various visual elements in such 3D physical space. In the final part of this presentation, we'll talk about people and argue that modeling the interrelations among people and objects in the 3D physical space plays a key role for solving another crucial problem in computer vision and perception robotics, that is, human behavior understanding and prediction.